to everyone. It gives me an immense pleasure to extend a very warm welcome to you all for this one day international webinar on advanced functional materials organizing by Department of Physics, Gonzaga College of Arts and Science for Women.
Prayer is an action. It is the process of asking God to achieve our purpose. So, let us begin this program by seeking the blessings of the Almighty through a prayer song.
Be here with your presence. Fill me with your power. Live inside me. Welcome, Holy Spirit. Be present. Fill me with your power. Live inside of me. You're the living water, never drying fountain. Come to life, take complete control. Welcome, Holy Spirit. Fill me with your power. Live inside of me. Welcome.
Great men show politeness in a particular way, a smile fulfilled to assure you that you are welcome, and keep about the occasion as if you were a member of the family. Now, I would like to invite Dr. R. Dinesh Kumar, Assistant Professor, Department of Physics, to give a welcome address. Welcome you, sir.
A happy morning to one and all gathered here. At the outset, I take the deepest blessings of the Almighty to cherish this day with victory and glory. As it is rightly said, research is creating new knowledge. Today, the ultimate aim of this noble gathering is to provide knowledge among the thirsty minds. I welcome you all wholeheartedly. Primarily, I am indebted to welcome our college secretary, Reverend Mother C. Noel Rani, FSAG, on this occasion, who is in all the walks of our college towards successful activities. We welcome you, Mother. Behind every successful woman is a tribe of other successful women who have her back. Yes, our most respected principal, Reverend Dr. E. Gleta Sumangali, FSAG, is a powerhouse of love, nobility, and willpower with due respect. I take the honor of welcoming her. I welcome you, sister. We rise by lifting others. Our vice principal, Reverend Sister A. John Diana, FSAG, keeps this motto as her life motto. And now I take the pleasure of welcoming her. I welcome you, sister. A good leader is one who knows the way, goes the way, and shows the way. Our today's resource person, Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai, is great dynamic personality who serves his service in research for more than 2 decades. I welcome you wholeheartedly to this victorious gathering, sir. The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. Yes, our most respected resource person, Dr. R. Tangappan, Assistant Professor, Department of Energy Science and Technology, Periyar University, Salem, who has the trust for knowledge. Always, we are very blessed to have you today, and I rendered my warm welcome to you, sir. And I am honored to extend my warm welcome to Dr. S. Tamilarasan, Assistant Research Scientist, Arizona University, United States, who is a pride of our country, who serves there in USA, a good friend of mine and a kind-hearted person. I welcome you happily to this noble gathering. Then I am extremely indebted to welcome the coordinator, Mrs. K. Devi, Assistant Professor and Head, Department of Physics. I welcome you, ma'am. Then I am pleased to welcome the organizing secretaries, Dr. S. Cholan and Dr. M. Manivandan. Welcome you, sirs. And I am happy to welcome Dr. S. Shegar, Department of Chemistry, who is here with us and consented to deliver valedictory address. Welcome, sir. Then I take the great privilege of welcoming all the staff members of the committee to this webinar. Welcome you all. I am extremely overwhelmed to see a massive participants around the globe. I welcome you all, dear scholars, scientists, subject experts, professors, students from various colleges, stakeholders, and students of our college, media personals, and each and everyone gathered here. Once again, a cordial welcome to all. Thank you.
Thank you, sir. Leaders instill in their people a hope for success and a belief in themselves. Positive leaders empower people to accomplish their goals. It's my privilege to invite Reverend Dr. E. Gleta Sumangali, FSAG, our principal, to give the inaugural address. Welcome, you sister.
Thank you. Respected and loving Reverend Mother C. Noel Jani, Secretary, Reverend Sister A. John Diana, Vice Principal, Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai, Dr. R. Tangappan, Assistant Professor, Department of Energy Science and Technology, Periyar University, Salem, Dr. S. Tamilarasan, Assistant Research Scientist, Center for Materials of the Universe and School of Molecular Science, Horizon State University, Ms. K. Devi, Head of the Department of Physics, Dr. Dinesh Kumar, convener of this international webinar, Dr. Chorin and Dr. Manivannan, organizing secretaries, members of the organizing team, all the faculty members and students of this college, participants and research scholars from various colleges, greetings to all of you. It is with great pride I appreciate the convener and the members of the faculty for organizing international webinar on advanced functional materials, which is very relevant topic of the era. The Department of Physics in Gonzaga College is a pioneer department in triggering research trend without any compromise to quality. Keeping in mind the students who study in the college should get the exposure and a rich experience of learning. I hope this marks that this department will become a department of excellence within a very short span of time. I'm glad that this department is taking exponential growth in all areas of the academic and non-academic activities. And I'm happy about Ms. Devi, Dr. Dinesh, and all the staff members of the department who are very systematic, hardworking in realizing the vision of the department. I wish and pray for the grand success of this international webinar. With this remark, I just want to share with you that the ages of mankind are labeled by their dominant materials. The Stone Age, the Bronze Age, the Iron Age, and now the Silicon Age. Why? Because materials define the sophistication and wealth of the nation. Materials create wealth, improve our standard of living, and are key to meeting society's need, from national security and communication to health and housing. Traditional materials are primarily structural: steel, aluminum, concrete, polythene, glass. Although they are familiar, their properties have been improved drastically in the past 2 decades, while their costs have fallen and their production has become more environmentally sustainable. Novel materials are primarily functional with optical, electronic, magnetic, or biological properties or unique environmental properties, such as resistance to high temperature. National leadership in manufacturing and trade requires leadership in materials. Materials are essential throughout industry in fields such as telecommunication, healthcare, energy, and automobiles. In these and many other areas, materials with high added value and high functionality strengthen existing industries and preserve the jobs they provide while creating new products that enable the development of new industry and new jobs. In recent years, nanoscience and nanotechnology have attracted much attention and have posed much significant potential in many areas of societal interest. For instance, opportunities are presented for help solving global energy needs with environmentally clean solution, increasing the quality of life through improved medicine and healthcare, improving the productivity of agriculture, industry, and providing the benefits of information technology everywhere. Recent developments of nanomaterials had enabled ever clean clothes and nano biosensor devices. Functional materials can be any type of specially designated material with a determined function. Semiconductors, polymers, molecular crystals, or nanoparticles are good examples of them. It is their special physico-chemical property which make functional materials so special. A special type of functional materials are synthesized with a large surface to volume ratio in order to maximize their interaction with the environment. Typical examples are functional surfaces and functional particles. The research on their synthesis and their characterization is crucial for future technologies. Materials are vital as solution for many social issues and challenges. The future promises both the creation of these novel materials and the greater availability and affordability of traditional materials. The sustainability and quality of life of an increasing proportion of the world's population will depend on whether these promises are achieved. Our nation would be the leader in developing and applying these materials for the benefit of the entire world. I wish this virtual forum should lead to some fascinating discussion to attend to the problems and social issues and challenges. As material science underpins every product and process on which our modern society depends. I wish all the best and have productive deliberations. God bless all your efforts. Thank you.
Thank you, sister. A great mind produces great men, but only the heart is able to guide them on the best ways. It's my pleasure to invite Reverend Sister A. John Diana, FSAG, our Vice Principal, to deliver the felicitation. Welcome you, sister.
Thank you, Anita. To get the world class is absolutely essential to become an excellent innovator. Most respected Reverend Mother C. Noel Rani, FSAG Secretary, Reverend Dr. E. Glita Sumangali, FSAG Principal, Dr. M. Arivanandan, Professors at Anna University, Chennai, Dr. O. Thangappan, Assistant Professor, Periyar University, Salem, Dr. S. Tamilarasan, Assistant Research Scientist, United States, Convener of R&D, Dr. R. Dinesh Kumar, Coordinator and Head Department, Ms. Devi, Dr. S. Cholan, Assistant Professor, Dr. M. Manivanan, Assistant Professor, and Organizing Secretaries, Committee Members of Gonzaga College, Research Scholars, Professors, students from various college, and dear Gonzagaites, happy morning. I appreciate Department of Physics for organizing international webinar on advanced functional materials with the world-class people to enlighten the youngsters of today and who become tomorrow's innovators. Dear youngsters, if you don't try, you will never know. Whatever we enjoy today is inventions of someone yesterday. Everything is science because it solved the maximum issues which arose. The hardest became easiest, the unknown became known, the difficult became easy, and at last the very big world became a global village. It's only because of the science. The great thinkers became the scientists. They executed their ideas that became a great change. In simple terms, no matter how the idea big, only assumes the values when it's acted upon and brought to life. In a way, we are also think great, but we never realize its greatness because we are all very strong in our thinking side, but weak on the execution part. One of the German poets, Johann, said, whatever you can do or dream you can do, begin it immediately. Boldness as genius power and magic. Today's speakers get both right. They are superb strategically and brilliant tactically, more creative and really good at getting things done. So jumpstart your commitment of learning from the experts and execute them. Capture your wise ideas and bask in the glow of remarkable imaginative thought that has the power to improve how you work or the way you live. Reach down yourself and have a discipline to do whatever it takes to make that idea a reality because everything happens only by your move. I wish all the best to have a great session ahead with a special title of Advanced Functional Materials. Once again, I wish you all the very best. Thank you very much.
Thank you, sister. A really great person is the person who makes every person feel great. At the very outset, we welcome our esteemed and eminent speakers. Dr. S. Tamilarasan, Assistant Research Scientist, Arizona State University, United States. Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai. Dr. R. Thangappan, Assistant Professor of Engineering Science and Energy Science and Technology, Periyar University, Salem.
Dear participants, those who are all could not able to join in Google Meet, kindly use the YouTube streaming which was posted in the chat box for first two session. Kindly make use of it.
I heartily welcome Ms. R. Tanal, Assistant Professor, Department of Physics, to felicitate Dr. S. Tamlarasan, Assistant Research Scientist. Welcome you, ma'am.
Pleasant and graceful morning to each and every one of you. I am very glad to have the opportunity to introduce Assistant Research Scientist Dr. S. Kamlarasan. He has a great understanding of the program and a great appreciation of what it takes to truly make one-day international webinar on advanced functional materials on a path of progress. Dr. S. Tamilarasan acquired his BSc Chemistry and MSc Chemistry at Sacred Heart College, Tripattur. He worked as a project assistant in Sikri, Chennai during August 2009 to February 2010. He obtained his PhD degree from Indian Institute of Science, Bangalore in the year 2016. Then he moved to the University of California, USA to do his postdoctoral work in thermochemistry lab in the year 2017. He joined the School of Molecular Science of Arizona State University, USA as an assistant research scientist in 2020. He has made a significant contribution to carry out synthesis, characterization, and thermochemical properties of inorganic crystalline and amorphous materials of interest in clean energy and functional applications. He has over 28 publications in international and national reputed journals with high impact factor. Sir have been invited to review manuscript in peer-reviewed journals for several times. He qualified national eligibility test conducted by CSIR in July 2010. He got 6 out of 593 in all over India. He continues to work in School of Molecular Science. With great patience. We are so blessed to have such a renowned person who comes to the level of us, eager to contribute his multidimensional talent for the development of us. I am delighted to extend a welcome to our chief guest, Dr. S. To take question. Welcome you, sir.
Thank you, madam, for your kind introduction.
Tamilarasan.
Can you all see the screen?
Yes, sir, it's visible.
Okay, let me go into the mode. Give me a second. Okay. Can you hear me?
Yes, sir, it's audible, sir.
Okay, I'll start now. So the topic I chose to present today for this webinar is energetics of nanosulfides. But my topic is going to be a little bit broad in the sense I'm going to speak about materials science and solid state chemistry structures, and finally I'll present something about energetics of nanosulfides, which I have been dealing in past maybe like 2-3 years. So my talk is gonna be like this. I'm going to present my research work uh, since from my graduate school, which is PhD, and then I'll present what I did during my postdoc at University of California, Davis, and what I'm doing right now. I am in the sense we are a large group. I'll mention everyone's name when I present the results. Okay. So this is Indian Institute of Science, Bangalore, where I did my PhD. Most of you might know that place. And my PhD thesis was not on nanomaterials, but on advanced functional materials. But when we tried to synthesize compounds, most of them are metastable, and we could stabilize only in nano phase. That's how I got connection with nano to begin with. Now, my thesis was based on pigments. Pigments are colored inorganic solids that has scientific, technological, and cultural importance. To say the very first materials synthesized intentionally by humans are pigments. The very first pigment was Egyptian blue. These and Chinese Han purple, both are synthesized by humans, very first materials. And if you can see, the molecular formula of these pigments are almost same, except one has calcium, other has barium, but in both copper ion is source of the color. But what makes difference in the color? One is blue, other one is purple. Though related, it's a difference. It's a difference in band gap. What makes it? If you look at the structure very carefully, in Egyptian blue, copper is square planar coordinated, and it gives rise to blue color. But in in Han purple, copper is again square planar, but these square planes are very closely placed in the sense it makes fifth metal-metal bond that changes the band gap, apparently giving a different color. So little change in the coordination environment changes the color, which means changes the band gap, semiconducting properties, catalytic properties. That gives a lead to investigate more materials. So what we did basically for my PhD thesis was take a material that has no color, in the sense it's white, having band gap more than say like 4, and dope some transition metal atoms, ions, which are partially filled, that would give rise to electronic transition between valence state and conduction state and create colored materials. When we went through the literature survey, we found this a very interesting material where which is YINO3, where indium has 5 coordinated compound and indium is in 3 plus. When indium is substituted with little bit manganese 3 plus, it gives very beautiful blue color, which is interesting because manganese 3 plus, if you look at it, always has dark color, band gap less than 2 electron volt. But how can this happen? And when these scientists try to understand what is happening, they figured out that the local coordination environment in this material for manganese is trigonal bipyramidal, which is 5 coordinated, rather than 6 coordinated octahedra that gives black, the dark color. Here it's trigonal bipyramid, giving rise to a different kind of electronic transition that gives this beautiful blue color. We took that as a lead, and we took a different host material which is white in color, YGaO3, instead of indium gallium, and we do manganese, and we hope we would get blue color, but we got purple color, like the difference between the Egyptian blue and Han purple. And then we investigated why is this happening. And usually when we characterize the colored materials, we use UV, visible absorption spectroscopy, to characterize them. And here you could see it's an absorption. We measure in reflectance mode and then convert to absorption mode using Kubel-Kammang function. And then you could see there is an absorption band. Let me have my laser point, which I should have done far before. So it has absorption around in the red region, leaving a window in the blue region. That gives rise to the blue color for indium material. But for gallium material, if you could see this, the second absorption shifted a little bit. Also here, the first absorption shifted a little bit. It little bit leaves a window in red region as well. So the combination of both red and blue color gives rise to purple color. So why is this happening? And when we look close in the structure and environment, it's same 5-coordinated environment. It's trigonal bipyramid. But when we look very closely, these 3 equatorial bonds are almost similar as in indium compound, but the axial bond is smaller than in indium compound, which means the chemical pressure is more, and that gives rise to the difference in the color and eventually in the band gap. So what we found is manganese 3 plus in trigonal bipyramidal geometry gives an unusual blue color and purple color. So what about other 3D transition metals like iron, cobalt, and nickel, copper in trigonal bipyramidal geometry? Will it give any new color, interesting color, rather than what we usually observe? Let's see. So we found this material LiMgBO3, which is again white in color with band gap more than 4 electron volt, and its crystal structure and other stuff. You can just go back into my profile and also contact me if I can give you more details. We chose this material and then decided to dope divalent transition metal in place of magnesium. And we begin with copper 2 plus, and we used flux method, flux in the sense Li lithium borate as flux to make these compounds that made nanomaterials. In pure phase, I'm not showing XRD and anything because I don't want to bore you with more technical information. And we characterized with color with again UV visible spectroscopy, and you could see it absorbs the whole red to green region, leaving window here, and that gives rise to color. And then we assigned electronic transition, all these things you can see here, and we doped nickel and got this amazingly beige red color, which is unusual for nickel. The only other compound that has been reported was this composition, which is more like perovskite. And again, here the reflectance window is in red, that gives rise to red color. And we assigned transitions, we calculated several stuff all in my publication. And next we wanted to explore what about distortion. So we saw a different coordination giving rise to different colors. Is there a question or something? So what about distortion and disorder? So we chose a material, host material, lithium, alpha lithium zinc borate as a host that has highly distorted coordination environment, also with a disorder between lithium and zinc atoms. we doped and we got this beautiful bright blue color. The when we characterize the color, we found that the brightness of blue color, look at here, the brightness of blue color for this compound is very high compared to the classical cobalt blue, which is the blue pigment used for like almost several hundred years, and also the newly found the very first the compound I presented in the first slide, or first part of this in this talk. Compared to both those compounds, brightness of this blue color was like so high, and we could publish in Chemistry Asian Journal this work. And interestingly, for nickel, we got this very nice pink color. Again, it's due to the distortion and disorder that uh, creates difference in the electronic transition, because you break the symmetry, and that gives rise to different electronic transition. And for copper, we got this very nice blue color, which is not interesting because copper usually forms blue color, but still we just assigned all the electronic transitions and published it. So now comes the advanced functional materials part of my pigment work. There is a concept called cool pigments. What are cool pigments? Cool pigments are smart materials. You take these pigments and introduce in your painting materials, right? And then you paint them on rooftop or vehicles like car, or military vehicles like military tanks, right? And what should this material do is selectively absorb the sunlight in the visible region and selectively reflect the IR radiation that creates heat during the summer or long exposure to the sun. Because when we say about roof getting or house getting heated during summer, it's basically the IR radiation from the sunlight that causes this heating. So we want a smart material, which we call cool pigments, that selectively absorbs sunlight in visible region and selectively reflects sunlight in infrared region. That's a new concept, and we were curious how good our materials would be, and we found that the reflectivity in the IR region for this material is almost like, for cobalt doped it was like almost 70. For nickel doped it was almost like 60, which is very nice compared to copper that doesn't reflect, but still you can see this absorption in the visible region and reflection. Absorption here, visible region, and reflection in IR region. So that's a cool pigment. And then we wanted to further investigate what we would get in a distorted octahedral environment. Octahedra is a very common coordination geometry we would encounter in most of the materials, but still, if it is distorted, what would be the color of common transition divalent metal atoms? And we proceeded with doping cobalt in zinc position and got this nice purple, violet, purple, blue. And as usual, we characterized it and then assigned electronic transition. Everything was good, and went to nickel, got this very nice yellow color. Very unusual for nickel to have yellow color, at least in inorganic solids, at least in oxides. So again, we characterized, did some DFT calculation, which I'm not showing here, to show electronic transition. All these different colors are due to the distortion in the octahedra. And nothing interesting with copper. It's just a green, light green color. And we went to next. We found a very interesting material that has been used in electrochemistry, Li2M1O3. with its defects, it shows electrochemical activity which is not supposed to show, but due to the defect and difference in the oxidation state, it shows some good electrochemical activity. But interestingly, for in the color science point of view, or catalyst or semiconductor point of view, this compound is red in color with band gap around 2 electron volt. No one has, this compound has been known like several years before, but no one cared about its color. But we wanted to follow up about its color and what is the reason for its unusual color, because manganese 4 plus is supposed to be dark brown or black in color. So we synthesized 4 different samples using 4 different methods: solid state, flux, just sol gel, and combustion, something like that, with a different temperature. No, these are 2 different temperatures. Yeah, so we did like that, and then we got the same compound Li2 MnO3 with nothing, no doping, nothing, but different shades of red, with this one having orange mostly, and this one being more like hematite red in color. And we characterized it and then found this material having orange color is really nano in size. And then we characterized its color using UV visible spectra, and then calculated band gap, plotted this tau plot, and that shows sample that was orange in color has electronic band gap very less than the sample that's red in color, this one. And it's basically the smaller particle size having lower band gap, the nano, classical nano stuff. And we could not do any calculation and other stuff using DFT, but we wanted to wind up this work, and we just proposed that in the structure of Li2 MnO3, in the transition metal layer, we have this very nice honeycomb layer ordering, which is like 1 lithium octahedra surrounded by 6 manganese octahedra, and it's repetitive across the lattice. We propose that might be reason for this color property, but we are not sure. So during my PhD studies, these are different colored materials we formed. Fortunately, we could characterize this red color is very rare in nature to find. Usually red colored materials contain toxic elements like mercury. So we said that this is a non-toxic red colored material, and also we made this compound with very bright blue color, brighter than the classical cobalt spinel. So going back to ancient materials, we usually think ancient materials are just made like ancient humans. They just deliberately made things, deliberately did stuff, which is true. In this case, it's often they made sample deliberately, in the sense they just mixed and got some color. Later they wanted to get this color, so intentionally they synthesized these compounds again and again. So it was half and half. It was half deliberate, half intentional. But when these compounds are made almost like 2500 300 years before, right? And the recent science found these compounds are very, very interesting. I'm not going to go into very detail into all these things, but let me just read the title, what they found after 3000 years. Exceptional near infrared luminescence properties of Egyptian blue. Basically, it's they take material, do exfoliation and make nano, and then see this amazing new property using spectroscopy. New life of ancient pigments, application in high performance optical sensing materials, and nanoscience of an ancient pigment. Basically, they You can see here they make two-dimensional layers from this material, and then they did photoluminescence studies and found some amazing, interesting properties. And near infrared emission photon energy of conversion of two-dimensional copper silicates, which is again related to Egyptian blue, you can see here. And structure properties of Egyptian blue monolayer family. Here it is monolayer. And some just same material using for some photonic studies. Yeah, and several more. And then you could see this Nature paper, dimensional reduction at a quantum critical point, complete physics. And material was again Egyptian blue. So ancient material getting interest from modern scientists. That's, I would wind with this theme of my first part of the talk. I have, like I said, I have 3 parts, and I finished almost half of my talk, and rest I'm going to present about the science what I did in United States of America during my postdoctoral day as a postdoctoral researcher and the current position. So I finished my PhD in December 2016, and I got an offer from Professor Alexandra Nawrotsky to join UC Davis in the Peter A. Rock Thermochemistry Laboratory as a postdoctoral researcher. And yes, I studied thermodynamics and thermochemistry, but I never did any experiment. I was excited to join. I was newbie, but still, you know, I had courage to join and pursue what is going to happen. Just interested. So what do we do in thermochemistry laboratory? We do experimental thermodynamic works. We do these experiments using several different calorimeters. Especially, I will show you this particular calorimeter, Alexis, which is high temperature oxide melt calorimeter, that measures enthalpy of formation, which is an important term in Gibbs free energy of formation equation, right? Along with T delta S, which is dependent mostly on entropy, change in entropy. So basically in this equation, enthalpy of formation is the deciding term unless a material is stabilized by entropy, like a high entropy alloys or multi-component alloys, multi-component oxides. These are entropy stabilized. Unless the compound is such kind, most of the compounds stability is decided by the delta HF, enthalpy of formation term. So how do we measure this? We measure by, like I said, it's a drop solution method. What is drop solution? Take a glass of water. This is an analogy I give to everyone when I speak about calorimetry. This is the simplest one I could find. People might differ, but just I'm telling my point of view, my analogy. You take a glass of water, put a spoon of rock salt, which is table salt, sodium chloride, with some inclusions, or sugar crystals, and you just stir it up. What happens? It dissolves, and you would feel chillness, which means it took energy to form. I mean, it took energy to dissolve, which is destruction. If it took energy to destroy, then it would release energy when it formed. That's all we do. We do using a thermochemical cycle, but salt like sodium chloride, sugars, these are easy to dissolve in water at room temperature. The real material what we use, for example, in your mobile phone, in the battery, you have most likely lithium cobalt oxide or some compound derived from lithium cobalt oxide, which should not dissolve in water. And how do you want to measure? How you can measure the formation enthalpy of this compound? So we have methodology. We have some compounds which we call solvent because they become liquid at around like 700 800 degrees Celsius, but they are solid at room temperature. And this compound, most likely, not most likely, it's specific, 3Na2O 4 MOO3, it's a sodium molybdate solvent. And we take this solvent to high temperature inside the calorimeter. This is the calorimeter. This is heart of the calorimeter, where you have solvent in the glassware. The glassware is like 4 feet tall. This part is hot at 700 degrees Celsius. Above this part is insulated. So this part is at room temperature. And this part is at high temperature and surrounded by thermopiles. That's the logo of thermochemistry lab. It's in the star shape and they are piled up like 127 or something. And it's a 3-dimensional sensor. It senses any change in heat flow. Now, what happens here is you drop the sample here. Rest is like sodium chloride in water analogy. It just dissolves. And when it dissolves, either it takes energy or releases energy. And we get this as a signal. It's my own compound that has both exothermic and endothermic signal, because endothermic is due to the uptake of heat and then it dissolves slowly. So it has both steps, but most likely usual experiment will have only one direction step, one step in one direction. So this is how we measure. And then what you do is if you want to measure the enthalpy of formation of a compound AB, you should have drop solution of same method. You drop and measure the drop solution of A and the B separately and the compound AB. Now, when you do a thermochemical cycle, the excess energy or the deficient energy is going to be the enthalpy of formation. If it is excess, if it is negative, the compound has exothermic enthalpy of formation, which means it's stable. If the compound has positive enthalpy of formation, it's not stable. With respect to these two components, enthalpy is always respect to something. It's a relative term. So that's how we do this, and we produce a lot of data. Professor Alexandra Narodsky is famous for drop solution calorimetry and thermodynamics. I'm very, very happy and honorable to work in this lab for so long time. So this is the calorimeter. This is side view. This is top view. You can see it's with glassware. You can see the glassware here, and everything happens at deep inside the calorimeter here, which is again insulated, and then it has furnace, a large controller to maintain the temperature, because these are highly sensitive experiments. And then we have computer here in this direction, and that records all signal. Now, again, going back to solid state chemistry, it might be boring, but still fine. You guys might end up dealing with this stuff sometime in your life. So what the family of, I want to give an introduction to the family of compounds I started to work in the thermochemistry lab at USA. So these are related to fluoride structure. So I was working on pyrochlore, which is related to fluoride, but you have multiple anions, and then they are ordered or disordered, and then especially Weberites, because these pyrochlores are used for some kind of nuclear waste applications, and they want to study what radiation does to this material structure. So you take a material and then exposed to radiation like nuclear radiation, right? High energy. What does it do to the structure? It basically amorphizes at X-ray level, at like X-ray like Armstrong level. But if you go to neutron level and check, they form actually at X-ray level, they are amorphous, disordered. There are no crystalline structure, no long range periodicity. But you go to nano level, like several, like 5-10 nanometer level, and analyze with neutron powder diffraction data, they saw that they form related structure, nano domains of related structure, but different complex structure called Weberite. So we wanted to study, basically this is a description of pyrochlore. It's like formed with it's with A2B2O7. A will be like 3 plus rare earth, B will be transition metal atom in 4 plus state, and what happens is A goes into like 8 coordinated, this large this large 8 coordinated position they take, and then they form like chain along with octahedrally coordinated B ions, and then they form this structure with this hexagonal tungsten bronze motif, and they repeat crystallographically all over the 3 dimension. So we studied related another structure. It's called zirconolite. I synthesized this compound and then measured its drop solution. And you could see I was studying something called enthalpy of mixing, and we did all this very nice work. That's one of my projects I like among with several, and this is the Weberite I was speaking about. So in the nano domains, you take pyrochlore material and you expose it to high energy radiation. They become amorphous by XRD characterization, but they form nano domains of Weberite structure in the in nano domains. So we wanted to take the Weberite structure itself, which is Re3Ta07, and then wanted to synthesize and measure, which I did, and then you could see we correlated enthalpy of formation data along with pyrochlore and Weberite. We found this Weberite being the most stable among all, which is not good news for using as host material for nuclear waste, but still it's a result. And then I worked at UC Davis from 2017 to 2020, and around 2019 my postdoc boss Alexandra Naurotsky opened a news that she's gonna move to Arizona State University to open a new center and become a director for that. So she gave a choice whether to come with her, move with her to Arizona State University, or I can search my own path. But I decided to move because why not? I thought it's gonna be interesting, and which was interesting. I'll tell what happened. So here is where I got introduced to nanomaterials, not oxides, but sulfides. So like in this schematic, you could see you can make nanomaterial, like I previously said, take a bulk material, ball mill it, high energy ball milling, and then make nano, or take a bulk material and expose to high energy radiation and form nanomaterials. Of course, I said amorphous, but still it's nano in neutron by neutron diffraction. Or you take atoms and then deposit them, physical layer deposition, atomic layer deposition, and then end up with nanoparticles again. What happens if what are we doing? We are just breaking up the material and create more surface, right? And all this surface has bonds which are unquenched, and these bonds give rise to interesting properties. So what are those bonds? Those are extra energy. What is that extra energy? Those are called surface energy. How can you quantify the surface energy? You can do DFT calculation, which is theoretical calculation. Can you measure experimentally, because we are experimental chemists? Of course we can, using our high temperature drop solution colorimeter that I introduced just before. So let me give a brief introduction on the material. We were interested in studying the surface energetics to begin with. So it's a iron thiospinel. Fe3S4, and it's a mineral named greigite. And it's structurally same, analogous to magnetite, which is oxide spinel of iron. It's an inverse spinel having half of the 3 plus in tetrahedral site and other half in 3 in octahedral site along with 2 plus, unlike normal spinel where you would find everything ordered. Anyway, so these are both naturally occurring minerals, and both are ferrimagnetic. Basically, they are magnetic. When the mineral is magnetic, they can be used to study the magnetic history of our planet. So you take those materials, that's called paleomagnetic recordings. You can study the magnetic history of our planet Earth, how the magnetic field of the core influenced the whole planet. And both of them can be, this is an interesting thing, both materials can be produced biologically by magnetotactic bacteria. Magnetotactic bacteria is something, I'm little bit tangential going to the biology, but still these bacteria produces materials that are nano in science. So we are still in nano regime, we are still in materials science regime. These bacteria take iron ions as their food, and then they form either oxide or sulfide depending on the bacteria. So it's just like bio-made nanomaterials. Interesting, very interesting. We are not yet exploring those things, but still very interesting. These are called magnetotactic because there was a biologist, scientist, they were trying to see this bacteria under microscope. The microscope had, no, they were seeing under microscope and they were orienting themselves into the magnetic field of our planet Earth. And they were like amazed, and then they said it's magnetotactic bacteria. And then when they investigated this bacteria using SEM and other microscopic technique, they found that they contain either magnetite or greigite or both of them together. And these materials, since they are magnetic, they orient to our planet's magnetic poles. So that's interesting. So the difference between them is they have different Verwey transition, which is structural transition from, since these two are metallic at room temperature, when you go down to low temperature, they become insulating material. So that is called Verwey transition, and they have different Verwey transition temperature. Also, iron oxide doesn't show any structural transition upon squeezing using high pressure setup, but iron sulfide shows a structural transformation around 3 GPa. It goes from cubic to monoclinic. So that's one difference. And Curie temperature of both of them differs. Of course, oxide is more stable, so when you heat them, it has Curie temperature higher. Also, another thing is metal oxygen bonding is different from metal sulfur bonding, which is more metallic, so they become maybe diamagnetic or paramagnetic at high temperature. Paramagnetic. Yeah, greigite. More on greigite. Greigite ought to be metastable phase because it was very rare to be found, and its occurrence was less than 100 places. And then also it was proposed to be a catalyst in during the early Earth, when they called prebiotic soup. Also, it was found in the famous Martian meteorite ALH 84001, proposed as, again, to be one of the reasons for magnetism in the planet Mercury. Anyway, our interest was to just measure its enthalpy of formation by enthalpy of drop solution. And we measured, we made bulk greigite, nano greigite, high pressure form, and measured all of them. it is obvious. You can see when it is more negative, it is more stable. Bulk is more stable than high pressure. Of course, high pressure is metastable, but look at nano. It is less stable than the bulk, right? Less stable, like 3 kilojoule per mole. Just that 3 kilojoule per mole is the excess energy that makes it less stable. And we have some number now, what some quantitative number about how much the stability has been lowered by number, right? Now you have number, and we use this thing, drop solution, because I said here for formation enthalpy, but if you look at drop solution, it's reversed, because stable the material, more stable the material, it's gonna give less exothermic dissolution, because it's gonna be less exothermic because it's stable, it's endothermic stuff in it. So we take the difference and you divide by surface area of the nanomaterial, you get surface energy, which is measured by experiment. And this surface energy is it's like no matter what the particle size is, you can measure surface energy. We determine the surface energy of nanogrigite for first time, that it's around like 1.15, which is similar to the nano magnetite and other spinels, which is not surprising, but still we measured it. And also we found that in the phase assemblage of iron sulfide phase diagram, grigite is stable with respect to decomposing into its neighboring phase composition like pyrrhotite or pyrite, and so we revealed that it's a stable compound indeed. And we went to study the high pressure stuff, and then we plotted temperature PT curve, which is like how the transition pressure changes with respect to temperature. Here it is negative slope, which means higher the temperature, transition from cubic to monoclinic is going to happen at lower pressure than at room temperature, which is 3 GPa. It's going to be at much lower pressure at higher temperature. So now what you saw is surface energy measurement using high temperature calorimetry, right? You can do surface energy measurement using another technique, which is called water adsorption or just adsorption calorimetry. What do? You have a porosity analyzer, an instrument, like, let me come back to schematic again. And this is porosity analyzer, an instrument with a port here. You put your sample, or first evacuate the sample, degas in the cells, remove anything on its surface, right? And then expose the surface. And then you go here, dose some gas, most likely nitrogen, and measure the surface area using BET technique. Now, we have a calorimeter. So we have a porosity analyzer that can measure surface area by dosing gases or vapors. Basically, it's interaction between the gas and the surface, exposed surface. And you have DSE, which can measure heat flow. When there is a change in energy, you can measure. Now coming back here, you have your material and you evacuate, and you have water, nanomaterial, right? And you have this setup inside this here in the calorimeter. What you do, you start to dose whatever solvent you want to interact with the exposed nano surface. Here they say water, but you can do alcohol, methanol, ethanol, and other organics. Just we are exploring because we don't want to expose this manifold into like some corrosive gases, but we can do several different absorbates on the surface. And when the exposed surface comes in contact with the absorbate, it's gonna absorb and give and it's gonna get quenched exothermically. So you get an exothermic peak which you can measure, which you can quantify, and from that there is a process you can get surface energy, right? And this is an example of two materials. So both are done with water absorption calorimetry. So you evacuate the sample overnight, expose the surface, and then you start dose uh, point or 10 micromole of water, one dose for 1 hour, second dose, third dose, fourth, five, and several doses. And around here, when you can integrate these peaks and see, right, around somewhere here, when you keep on integrating, you are supposed to get integrated value more than enthalpy of condensation of water, because we are dosing water vapor and it interacts with nanomaterial surface and it forms a kind of bond, and it keeps on does several layers. When you complete all the exposed surface by dosing water, right, after that, if you dose, what happens is water just condensates. There is no interaction between the material and water. It just condensates as water in liquid form. So when you keep on integrating these peaks, when you integrate and get minus 44 kilojoule per mole, which is enthalpy of condensation of water, that's where we draw a line saying that the interaction between the surface of nanomaterial and water has been done. And then we integrate all the peaks before that, and then we have special calculation. By that way, you can calculate surface energy of exposed surface, like anhydrous surface. The one we previously measured using Alexis is surface energy of hydrated surface. If the surface had water, you drop with water. Here, the surface doesn't have water because we evacuate the water overnight by heating. And this is another material where dosing or the surface got saturated by maybe like by 6th or 7th dosing, unlike here, which went up to like 20-25 doses. So what is interesting, like principal said like materials are everywhere. Now everywhere, even outside the solar system, everywhere in the universe, you deal with planets, you deal with asteroids, you deal with meteorites. Materials are everywhere in the universe. That's the new concept that lured me from UC Davis to Arizona State University with my professor. It's the concept called materials of the universe. What about, we know characterization. We make new materials. We make them in different forms, nanoforms, different polymorphs, and you measure them, you characterize them, get different properties. That's a direct problem. It's a direct problem. What about you have an inverse problem? You have a material, you know the property, you can measure the property, and you backtrack what that material is. That's how space exploration happens, right? You go to Mars and measure its property, and then based on the property, you know what material is there, because we cannot go there yet. So that's material of the universe. At least we are confined just to the few planets right now, but with our telescope evolution, we can explore several different planets outside our solar system using transmission infrared spectroscopy, which is fascinating and amazing. So that's gonna be new direction, one of the new directions for materials. So nanomaterials are found in exoplanets where temperature is very hot in the surface. As you approach cooler temperature, they just nucleate and then form nanoparticles. And what kind of polymorph it forms depends on the surface energy. So surface energy is important. That's where we are still working on several stuff which I cannot apparently present. That's why my talk and title little bit contradicted, but still if it is very diverse, I apologize, but still this is the concept we are going towards, and it's very nice and fascinating. By this, did I finish sooner? Anyway, I'm trying to present for 40 minutes. So I thank Professor Gopalakrishnan, who is my PhD supervisor, along with Professor Narajan. Both are co-PIs for me, and Devajit Sharma, my senior, now professor at IIT. Sauralaha, my colleague, my grad school mate, now assistant professor at NIT Durgapur, and that's my IIC life. And this is my postdoc life, where I thank my Professor Alexandra Navrotsky and my colleague and friend Kristina Lilova and my colleague and friend Sergei Ushakov. And you can more find about materials of the universe if you are interested in this link. Maybe I should post in the comment. Thank you. Questions?
Hello?
Yes.
Can you able to hear me?
Yes.
Yeah, it was nice presentation. Thank you, Dr. Krishnagiri. So I would like to ask a few questions, maybe fundamental. So you were talking about iron oxide and iron sulfide. So then you come to the surface energy of iron sulfide. So when you tell the enthalpy of, when you speak about the enthalpy of formation, so in comparison, oxides and sulfides, oxides will have higher energy. Am I right?
Yes, in one
Because
sense.
since it requires high temperature, it may require the formation energy also higher. But in case of
Yes.
surface energy, how you could compare and how it is related one among other in terms of surface energy, as well as when you bring it back to the nano size, both in bulk as well as nano.
Okay.
Hope you
So
got my question.
yeah, I got it. Let me answer. So when we speak about formation enthalpy, it's about the bulk per mole. So the bonding, each bond between iron and oxygen is completely different from each bonds between iron and sulfide, in the sense iron sulfides are more covalent bonds, iron oxides are more ionic, so you are going to have more exothermic, definitely yes, more exothermic formation enthalpy. But let's come to just surface, that's bulk. Even in a nanoparticle, the core is gonna be same, it's gonna be like bulk. The only difference is those bonds exposed on the surface, right? So if you see, say like you have 100 bonds on the surface of nano oxide, 100 bonds on the nanosulfides, that difference is not gonna be huge, because that's within like small error. So that's why you see similar surface energy. I hope that answered the question.
It's time for asking question. If anyone wants to ask question, you can proceed or type your question in chat box.
thanks for the explanation. So I can ask one more simple question to you. So when you are talking about the pigments, especially you have shown lithium manganese compound, and also you have shown yttrium dope manganese compound. So in case of certain luminescent materials, when you compare rare earth activator and manganese, like rare earth activators, the manganese won't give unless otherwise it 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 goes to the, or it is in reduced form. So how we can make manganese as a luminescent material or manganese doping, as well as directly you have shown some material showing the luminescent behavior, right? Instead of activator, even host itself showing luminescent behavior.
Yeah, it's called self-activated phosphors. There are like if you look at calcium molybdate, CaMoO4, these are very, very special rare compounds where you don't need that host dopant interaction at all. You don't need activator at all. These are special compounds where the compound itself is self-activating, and we have cited several things in that paper. I'm not remembering, but I can definitely say calcium molybdate to be one. But in lithium manganese, Li2MnO3, this is where question comes. Like, it's supposed to be not electrochemically active, but it showed electrochemical activity, and then they found that not all Mn is in Mn4 plus, as in the formula you have some Mn3 plus. So they said that Mn3 plus accepts electron, blah blah blah. So same might be applied here, that few amounts of Mn3 plus with one more electron could be activator, which is again, there is no dopant, it's self. But we did not explore it for we just characterized with like primitive techniques and published.
Thanks, sir. When you are telling about the oxidation state of Mn, so usually when you have Mn as a dopant, it will be present in +2, unless otherwise you reduce it to +4 or a higher oxidation state.
No,
is there
no, it depends. If you start with MnO2 as a starting material, which is in 4 plus, you would end up with 4 plus. And if you start with Mn2O3, it goes to Mn2O3. And Mn3 plus is the most stable form for manganese. If you want Mn4 plus, you have to do reaction in oxidizing atmosphere. At least I'm speaking about solid state synthesis. And if you want Mn2 plus, you have to do synthesis in reduced atmosphere. In typical solid state synthesis, we go beyond like 1000 degrees Celsius at least. But maybe by sol gel and other nano processing, you might stabilize Mn2 plus, but that's a different story.
Thank you, sir.
Thank you, sir. It is very useful to me. I have one doubt. What is the major difference between pigments and luminescence materials, sir?
So pigments are just visible reflecting material, like it reflects light, right? And luminescent material have fluorescence. they go to fluorescent state, I think, if I'm correct, but I never thought about this. It's a fluorescence, it's a different property itself. It's like fluorescence and phosphorescence. So in pigments you have electronic transition between valence and conduction band, right? In luminous material it goes to different state and then it comes back. I'm no good in that, to be honest. But that's the basic difference, if I'm correct.
Thank you, sir. Sir, there is a question from participants via chat box.
Yeah, sure.
So Sabarina
Thank
then
you
has
so
asked,
much.
can you say surface free energy and surface energy are same or different?
Yeah. From Sabarinathan, can you say surface energy, free energy? No. Free energy is completely different concept. Free energy is when you have A and B, how much energy it requires to form as a compound. You have component A, component B. If you want to make a compound out of them, what it is, whether it's gonna be like gonna go to the lower energy state than the components, or it's gonna end up in higher energy state than the component. That's free energy, gives free energy. Surface energy is completely different. It's just it's not free bonds, it's unbonded bonds that will be stabilized by something. It cannot be left unbonded. It will be stabilized by something. In this case, what I showed, take an oxide, TiO2 or zinc oxide, water will stabilize those bonds. And for that stabilization, there will be it cannot be free energy, but it's just like, because we are not forming a compound, it's just like a absorbent nanoparticle interaction. It's not a real bond, right? It's just like van der Waals forces. So free energy comes when the real bond forms, either ionic or covalent, even metallic.
Thank you, sir. If there is any other question from the participants, can ask your questions by one. Dr. Rajaganapati has raised your hands. Sir, can you ask your doubt, please? Anybody have any other queries? If there is no more queries, let's go for the next section. Over to MC section.
Thank you, sir, for your wonderful presentation. It was very useful in our future career. Let us start the second session. I extend my warm welcome, Mrs. Organimari, Assistant Professor, Department of Physics, to felicitate Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai. Welcome you, ma'am.
Good morning, one and all present here. It is my great honor and pleasure to introduce the speaker, Dr. M. Arivanandan sir. He is working as a professor at Center for Nanoscience and Technology, Anna University, Chennai. He has completed his PhD in physics at Alappa University, Karaikudi, on unidirectional growth of novel organic crystals. Sir's passion on teaching made him to start his career as an assistant professor at Research Institute of Electronics, Shizuoka University, Japan. He has been a visiting associate professor at ICC IMR, Tohoku University, Japan. His contribution is more. Am I audible? Am I clear to every one of you?
Yes, ma'am, you can
Oh,
continue.
okay. Thank you. Sir, contribution is more in the research field. He has more than 20 years of experience in physics of crystals. So, is there any cross talk? Sorry. Am I audible? Am I
Yes,
clear?
ma'am. Yes,
Okay,
ma'am, you
okay.
can continue.
Okay, sir. He has more than 20 years of research experience in physics of crystals, thermoelectrics of bulk and nano materials, and defect engineering in silicon and silicon germanium alloy semiconductors. Sir published more than 203 papers in international journals, 51 papers in conference proceedings, also presented more than 400 papers in international and national conferences, seminars, and workshops. He has delivered more than 105 invited talks, lectures in various national and international conferences at various countries. Sir has guided 7 PhD scholars and 8 research scholars are working under his guidance on nanostructured alloy semiconductors and oxide semiconductors for energy conversion and energy storage applications. Moreover, he has received several sponsored major research projects with a total grant more than 17 crore rupees funded by various organizations such as DST, SERP, STARS, MHRD, MEXT Japan, GIMRT Japan, and JAXA Japan. He is a Board of Studies member for various institutions in India, including Wales University and Loyola College, Chennai. Currently, he is having 2 national projects and 2 international projects. He received many awards and recognitions. I feel proud to share the awards. First, he received Distinguished Researcher Award by Anna University in September 2021. ISPA Dr. S. Gunasekaran Award by Indian Spectrophysics Association in January 2020. Young Scientist Award 2018 in Physical Sciences by Academy of Sciences, Chennai. Young Achiever Award, Ilavenil Science Association, Chennai. Early Career Research Award, SERB, DST in India, June 2016. JSPS Young Scientist C Award in the academic year 2014 to 2016 from MEXT, Japan. JSPS Young Scientist B in the academic year 2010 to 2012 from MEXT, Japan. He is a coordinator in Erasmus project with University of West Attica, Greece. And also, he is an editorial board member of the journal Crystal Structure Theory and Applications from August 2012 onwards. He is such an eminent personality, and today he'll be sharing with us his expert opinion on the nanostructured materials for energy harvesting applications. With that, I ask that you pay your full attention to acquire more ideas from our chief guest, Dr. M. Arivanandan sir. I hope it will be useful for the young researcher. Now, I call Dr. M. Arivanandan sir, our chief guest, to take over the session. Sir, welcome you, sir. I thank you, one and all present here.
Thank you, ma'am. Thank you for your kind introduction. Can you see the slides now?
Yes, sir, it's visible, sir.
Okay, fine. So,
So can you go for a full screen mode and then show?
yeah, I'll go. Please
Yeah.
wait. And,
Yes.
please all of
Thank you.
you, everyone, and let me start my presentation. Before going into the presentation, I'd like to thank the organizers, Dr. Dinesh and his team members, for inviting me to share some of our research activities in this international webinar. And I appreciate the team of this college for organizing such a wonderful webinar, and it will be useful for the young researchers to get more exposure about the recent trends in advanced functional materials, and hope you enjoy today's webinar. So, as a part of this webinar, I'm going to give a talk on this nanostructured materials for energy harvesting applications. Let me start with this slide, that means the global warming. So, everybody is, knows about this global warming, and this global warming is originated from the greenhouse effect. Of course, this is one of the very useful effects. So this effect is quite useful for humans to live in the earth with more comfortable, right? So if there is no greenhouse gases, if there is no greenhouse effect, then I think you know what would be the temperature of the earth, right? Or if you didn't know just Joule, then you can understand the importance of this greenhouse effect or greenhouse gas. But what happens in the recent decades, the density of these greenhouse gases are increasing enormously in the atmosphere of this planet. So that's the issue. So because of this high density, the re-radiation of solar radiation is also increasing, and that increases the temperature of the planet every year. And that kind of rise of temperature of the planet leads to a lot of subsequent effects in the lifestyle, human lifestyle, as well as the ecosystem. Especially the polar regions, there are a lot of ice rocks are melting. And these kind of ice rock melting will give you subsequent effects like sea level rise and other issues. So when the sea level rises, of course, as you know already, we have only limited land surface. Only 1/3 is land and 2/3 are covered by the water, right? Then if the sea water level rises, then the land surface, the landscape will decrease reasonably. So that will lead to lose a lot of land spaces, especially near the seashore region. So that's what is happening, and it's going to happen in future as well. And recently you may heard in the newspaper that even in the southern part of the country, the seashore, near the seashore regions, most of the land surfaces may go under water based on the global warming. So like that, some kind of predictions are there, some kind of alarming situations are there. So all these things are originated from this global warming. And look at that, this is one of the research group from University of Edinburgh and University of Leeds. They studied, they conducted a systematic research on this ice rock melting, and they predicted that more than 28 trillion tons of ice is almost lost for the last 3 decades. So this is really in a huge scale. Okay. So this level of ice rock is melting, keep on melting, then definitely all the things will happen, like the landscape will decrease for the period of years in the coming future. And this is another news which is published in Tamil News Daily, and it's almost in last year. And they said that ice rock was recently melted in the Antarctic region, and the size of the ice rock is more than 3 times of the size of Delhi city. So just imagine the size of that rock which is melted in this sea. And remember, this is the second one. The similar size of the rock was melted a few months ago of this incident. So if this kind of huge level of melting occurs, definitely that will give a huge impact on the sea level, right? So that's the what is happening at the polar region, and this is the simulated data of the temperature of our planet as a function of years, and this is simulated by the Earth simulated software, and this is simulated by the people from the Yokohama Institute for Earth Sciences, Japan. And maybe you can go through their website, and they have shown it as a video, and you can get it. They have just taken a 3 snapshot of that video, especially at our country's region of the globe at the interval of 100 years. And look at that, the first one is the 1900, and second one is the 2000, and third one is the 2100. And the white spot is the normal temperature, and red spots are the hotter ones. And look at 1900, the red spot is very less, right? Especially near to our country's region. But when to 2000, the red spot is reasonably increased, right? That is about 2 decades before, right? And in 2100, look at that, almost most of the regions become red. So that's future. So they predicted the futuristic trend of this global warming and the subsequent rise of temperature on the Earth based on the available data. So they predicted that if the average temperature of the Earth is increasing in the current rate, it will reach like this situation. So based on this predicted data, the people are trying to give a lot of exposure, a lot of alarming conditions for the future, and based on that, a lot of governments and governments of developing countries and developed countries, and they are making a lot of rules and regulations and norms to control the CO2 emissions. The CO2 is one of the dominant greenhouse gases, and by controlling the greenhouse gas emissions, somehow we can help to control the global warming, and that will lead to keep our environment as clean as possible. And please remember, we are one of the leading CO2 emitters in the world, next to China and US. So, as this is our own responsibility, and each and every one of us should be responsible for this carbon emission from the environment. So these carbon emissions are from different sources, not only from power plants, or not only from industries. The emissions are occurring from different sources, like starting from automobiles to the industries, and to the power plant, and to the power engine, so like that, and forging, so like that. There are a lot of industries are there, a lot of usage sites are there. So everywhere the CO2 and other greenhouse gases are reasonably coming out, and they are simply going into the atmosphere, and that leads to improving global warming. So the aim is that to control the CO2 emission by reducing the usage of greenhouse gas emission system. And another thing is that the recycling of these kind of waste heat which are coming out from these industries. So these are all the industries like automobiles and the incinerators and some thermal power plants and the kind of industries. So if the waste heats are coming into the atmosphere, then it contains a lot of greenhouse gases that leads to the environmental pollution, right? So this is the data which is published by ACE Japan, and they said that more than 65% of the waste heat coming out from the industries become waste, so without any proper recycling. So if we can recycle these waste heat in a usable way, then somehow the emission from the waste heat can be controlled, and that will lead to control the environmental pollution. So the thermoelectric technology is one of the energy harvesting technologies, and by using that, you can able to recycle these waste heat which are coming out from different industrial sources, and in that aspect, it can able to control the environmental pollution. As well as from waste heat, it can able to generate the electricity, it can able to fulfill the increasing energy demand. So the energy demand is another aspect of another issue of this present as well as future generations. The two things are there. One is the environmental issues and the other one is the energy demand. So the people are working on different aspects to solve these two issues. So my talk is mostly on this energy as well as environmental issue. So the first part is the thermal energy-based energy harvesting, and the second part is the solar energy-based energy harvesting. Okay. So the first one is the thermoelectric, and for the thermoelectric, you can use this kind of technology to recycle this waste heat from the industries or the automobiles, and that way you can able to control the environmental pollution as well as you can fulfill the energy demand. How the thermal energy can be converted into the electricity? So look at that. This is the, maybe I hope you can follow the mouse arrow. So this is the pie-like structure. The thermoelectric people, they used to call it as a pie-like structure. And it has two legs. One is written as P and another one is written as Z, right? And they both are connected at one end and open at another end. And when you have the heat energy at the junction, then the respective charge carriers in the p-type and the n-type semiconductors will thermally accelerate and diffuse from hot end to the cold end. Then you'll have the potential at the cold end, and when you connect to the load, you can run the load using the potential. So in that way, you can able to convert the thermal energy into the electrical energy, and that way, you can able to fulfill the energy demand as well as control the environment. But this technology is not so new. Actually, this is the very old technology. People are using this technology for quite a long time, and from the Voyager spacecraft period, they have used the silicon germanium-based thermoelectric generators. And wherever the thermal energies are there, you can use the thermal energy to convert it into electricity by using these thermoelectric generators. And not only that kind of space-related applications, as well as for automobile-related industry. They used to call it as a catalytic converter. So they used to call the thermoelectric generator as a catalytic converter, and that kind of catalytic converter can be easily fabricated by using this kind of thermoelectric pellets, and by connecting these thermoelectric pellets in an array, you can make this kind of thermoelectric module, and this kind of module can be placed as a thermoelectric generators or catalytic converter in between the engine exhaust and the outlet of the automobile. And when you have this TEG, then the engine exhaust, which is going through the TEG, contain less pollution compared to the emission without the TEG. This is already proven. So that the people already they have installed this the catalytic converter in the luxurious automobile, and this TEG convert part of the engine exhaust thermal energy into the electrical energy, and that can be useful for the interior purpose of the automobile, and thereby it can control the emission as well, right? So like that, they have already installed this catalytic converter in many automobile systems to control the emissions from the automobile. And there are other strategies that people are following to improve the performance of these thermoelectric generators. Like the ultimate aim of generating electricity is to have by establishing temperature gradient between the hot end and cold end. Since the temperature gradient is the driving force for this electrical output. So as long as you have the temperature gradient, then you can have the electricity. So to establish the temperature gradient or to increase the temperature gradient, the people are trying to do a lot of innovations in the system. Like this is the thermoelectric generator, and at the hot side they used to put some kind of heater like burner box, and there you can able to increase a lot of thermal energy. And on the opposite side, you can establish some kind of effective coolant, so that they can have the large temperature difference between the hot end and cold end. That will lead to improve the electrical output. And these are all some of the commercially available thermoelectric generators which are available in the market. Even in online, you can buy these generators, and you can use it for demonstration. Okay. Apart from that, as I said, no, it's not only for thermal energy from industrial waste, as well as you can able to generate the thermal energy from the solar radiation. But the normal solar radiation cannot be useful to establish such kind of temperature gradient. Okay. Then you need a kind of strong temperature gradient. For that, the hot end temperature should be as high as possible, and that can be realized by establishing some kind of optical concentrators, like by using some kind of optical lenses arrangement, and they can able to convert the incoming solar radiation into the hot junction of the thermoelectric generators, so that the temperature of the junction can be raised, and on the opposite end, by establishing a effective coolant, they can able to reduce the temperature, so that the temperature difference will be quite high, and that will lead to improve the electrical energy output. And not only optical concentrators, as well as some kind of other optical arrangements like parabolic reflectors, and some kind of lens concentrators, and some kind of the multiple reflection based systems. So like by doing a lot of optics, we can able to convert the incoming solar radiation into the hot junction of the solar thermoelectric generator, and that can able to increase the temperature of the hot end. With the help of the effective coolant, we can establish the temperature gradient, and that leads to harvest the electricity. And this is another innovative approach, like the floating solar thermoelectric. So that means instead of installing a effective coolant, you can float the thermoelectric generators on the sea surfaces, and where you can able to have a kind of the heat absorber on the top that will raise the temperature at the junction, and then since the opposite end is directly in contact with the sea surface, so it's already cool, and they'll have an effective temperature difference, so we can able to have the thermal power conversion from the solar radiation. So like that, without coolant, just by floating on the surface, we can able to generate the electricity by using floating thermal electricity. So these are all the innovative approaches for thermoelectric technology, but the reality is not up to the level of photovoltaic. Like the silicon-based photovoltaics are a kind of well-established technology, and it's commercially available, and you can buy it, and you can install on your rooftop, and you can get electricity for more than 20 years. Although the lifetime of storage devices are at about 5 years, you can install the solar panel with the lifetime of about 20 years. But still, the performance of the thermoelectricity is not up to the level of the silicon photovoltaic. So look at that. This is the conversion efficiency relation of a thermoelectric generator. This is a function of two parameters. One is the ZT. The ZT is nothing but the figure of merit, and another one is the temperature difference between the hot end and cold end. And this is the theoretically calculated conversion efficiency as a function of two parameters. One is the hot end temperature, and another one is the figure of merit. And look at that. I just drawn one more line, horizontal to the x-axis, the parallel to the x-axis, and that is a dotted line. This here, and this dotted line is the conversion efficiency of the commercially available silicon solar cell, and it's about 20% conversion efficiency. So if you want to increase the efficiency of a thermoelectric module with the comparable efficiency of photovoltaic, then you need to go for temperature up to 1200 Kelvin with the ZT of about 1, right? But for that, your material should withstand up to 1200 Kelvin. Suppose if your material is not withstand up to 1200 Kelvin, even you can achieve the same conversion efficiency at almost half of the temperature of about 600 Kelvin. But for that, the ZT of your material should be more than 2.5, right? So like that, either by increasing the hot end temperature or by increasing the figure of merit, you have to increase the conversion efficiency. But the temperature, thermal stability and temperature is mainly based on the material and its molecular and atomic binding energy. so it cannot be modified further. But the ZT of the material can be modified through the material science and engineering, right? So that's what people are doing. So these are the strategies for improving the ZT of the material, how one can improve the ZT of the material. I just forgot to mention about the ZT. The ZT is nothing but the S square sigma by kappa and T, right? So the S is the Seebeck coefficient and sigma is the electrical conductivity and kappa is the thermal conductivity. So S square sigma by kappa means the figure of merit, the Z is directly proportional to electrical conductivity and the inversely proportional to thermal conductivity. All right? Yes. So if you want to have the high ZT, your material should have high electrical conductivity and poor thermal conductivity. But it's quite difficult to find such a material because according to the Weidmann-Franz law, the electrical part of the electronic part of the thermal conductivity is related to the electrical conductivity, right? That is, the electronic thermal conductivity is directly proportional to the electrical conductivity. So if the electrical conductivity rises, then the electronic thermal conductivity will also rise. So it's quite difficult to independently control the electronic thermal conductivity and electrical conductivity. That's a challenging issue in thermoelectric research. But this is the Weidmann-Franz law is valid only for metallic materials. When you go for the semiconducting material, the lattice part of thermal conductivity is quite dominant than the electronic part of thermal conductivity. So that's the main beneficial aspect of semiconductor. So that's what the people are working on, semiconducting material for thermoelectric rather than the metallic structure. So the semiconductors provides an elegant way for independently controlling the electron transport as well as the thermal transport. So that's the reason why the semiconductors are dominating the thermoelectric research. And another thing is that the lattice part of thermal conductivity is dominant in semiconductor as well as it is not at all related to the electrical conductivity. But how the thermal conductivity, lattice part of thermal conductivity can be controlled? Here is the relation. You can see the lattice part of thermal conductivity is a function of three parameters. One is the specific capacity of phonon and velocity of phonon and mean free particle. So when you have a nanostructured materials like this and with some inherent defects as well as some intentionally introduced defects, so these defects will create some kind of phonon scattering centers. So these defects will act as a phonon scattering centers and thereby they effectively scatter the phonons and thereby the phonon mean free path gets decreased and the lattice part of thermal conductivity can be decreased. So the only thing is that by correcting this kind of defects, by intentionally introducing this kind of defects, the nanostructured bulk material, one can control the lattice thermal conductivity and thereby you can able to enhance the safety of the material. And on the other hand, by doing the doping engineering and by doing the carrier concentration tuning, one can able to improve the power factor of the material. The power factor is nothing but the square of Seebeck coefficient to the electrical conductivity. And when you have the high power factor, then the ZT is also can be able to improve. So these are the two ways how the ZT can be enhanced, and with that you can able to improve the improve the performance of the thermometer. So these are all the strategies that people are trying to follow to improve the thermoelectric performance of the material. So they're reducing the thermal conductivity without degrading the electrical conductivity. And that's possible by defect engineering and the introduction of nano inclusions and all. And another thing is that the nanostructuring of the material that will is an elegant way for modifying the DOS and that will reach to independently control the Seebeck coefficient and the electrical conductivity of the material. And energy filtering effect is another important phenomena. One can use it for carrier selectivity and that will lead to improve the Seebeck coefficient. So the ultimate aim of thermoelectric researchers is to find a kind of a phonon glass electron crystal. That could be a this thermoelectric material, and these are some of the examples for such kind of phonon glass electron crystals, like high PCC conductors and a kind of complex crystal structures and the kind of zeolite-based structures. These kind of materials having kind of complex crystal structures with layered arrangements, and the layered arrangements will facilitate the electron transport, and the complex crystal structures will facilitate the phonon scattering, so that the phonon gas electron crystal behavior can be realized in this kind of system. And the nanostructuring provides the positive aspects for improving the for improving the figure of merit of the material, and these are all some of the proven reported data. So for electrolyte based systems, you can see the effective reduction in thermal conductivity in nanostructured material compared to the bulk material, and that way the ZT has been enhanced. And similar results have been observed in electrolyte-based lattices. There also the thermal conductivity is effectively reduced in nanostructured material, and that leads to improved ZT of the material. Right? So like that, the people are working on different kind of nanostructured materials, and these are all some of the low temperature and high temperature thermoelectric material, like telluride and silicon germanium, and apart from these two, like photodides and zinc antimony based intermediate temperature materials also there. And for a best thermoelectric material, the ZT should be greater than or equal to 1. And with that, if you design a material, then you can able to have some reasonable performance from that kind of material. And then recently, the thin telluride based material shows high performance, like IZT of more than 2.5 with intermediate temperature active region. And we are also working on different kind of materials like silicon germanium and thin telluride, selenide, and telluride, like that. I just want to show some of our activities on this thermoelectric research, and we just try to understand the impact of tellurium substitution on thin selenide nanostructure samples. For that, we prepared the thin selenide samples by ball milling by using the appropriate precursors, and just systematically varied the tellurium content in the thin selenide samples. And these are all the microstructures of the preferred material, which shows the high grain connectivity that would facilitate the electron transfer in the system. And these are all the structural features of the preferred thin selenide with the tellurium substitution. And look at that, the structural data deposit shows that the tellurium is completely dissolved into thin selenide lattice up to 10% of tellurium. And when the tellurium content increases beyond 10%, there is a secondary phase formation, which is mentioned here as a diamond symbol, and that's thin telluride secondary phase. And up to 10% is a complete solid solution with aligned characteristics, as the systematic peak shift is there. And these are all the chem images of this tellurium substituted thin selenide, and it shows the high grain connectivity and grain structures and the crystallinity of the samples. And the tellurium incorporation in the thin selenide has been confirmed by this phase analysis, and there is a presence of tellurium as well as current phase. And these are all the electrical characteristics of this thin selenide with the tellurium substitution. And look at that, the pure thin selenide shows relatively high resistivity, and when the tellurium content increases in the sample, the resistivity has been reasonably decreased up to several orders, and that's mainly due to the variation in the carrier density. The carrier concentration also measured for the samples. And look at that, the carrier density has been increased up to 3 orders, and but relatively high doping, high tellurium content, the carrier density is slightly decreased due to secondary phase formation in the sample. And based on that, based on the variation of carrier density, the Seebeck coefficient of the resistivity has been decreased. And these are all the pelletized nanostructured material which were used for this electrical and thermoelectric measurements. And these are all the Seebeck coefficient of this pelletized nanostructured tellurium substituted thin selenide sample. And the Seebeck coefficient has been measured by placing the sample between the heating and non-heating end. And look at that, the few sample shows slightly high sugar coefficient due to its high resistive nature. And when the tellurium content increases in the sample, the sugar coefficient has been decreased due to low resistive in the sample. And for the tellurium 20% substituted sample, there is an interesting phenomenon that the transition occurs from P-type to the N-type nature of the material, and that's mainly due to the tellurium deficiency in the sample, especially at high temperature, and that's possible when we heat it at a high temperature due to high vapor pressure of the tellurium in the lattice, and it's highly volatile compared to the rest of the elements. And the sugar coefficient is also, the inversely varying with the carrier density in the sample, and that's what obeys the mode relation, so that shows the reliability of the measured data. And from the measured sugar coefficient and the resistivity, the power factor of the sample has been calculated, and the power factor shows that the material is 10% tellurium substituted insulinate shows relatively high power factor compared to the rest of the sample, and that's mainly due to the few phase with complete dissolution of tellurium in the insulinate lattice. So the result confirms that the tellurium substitution at the tinselenite with reasonable percentage is quite beneficial for improving the thermoelectric characteristics. And similarly, we are working on some oxide thermoelectric materials, because why oxide means, look at that, this is already I have shown you, the semiconductor-based thermoelectric materials, and most of the semiconductor materials are quite active within the 1000 Kelvin, right? Except silicon germanium. Only the silicon germanium is the material which can withstand more than 1000 Kelvin in the semiconductor. But look at the next slide, next plot. This is the oxide thermoelectric material, and almost most of the materials are quite active even after 1000 Kelvin. But the thing is that the figure of merit is not up to the level of semiconductor-based material, right? The figure of merit, most of the material, the figure of merit is less than 1, whereas here it's most of the materials are more than 1. So that's why the people have started to work on oxide thermoelectric materials to improve their performance for high temperature thermoelectric application. So if the ZT can be improved further, then these kind of oxide materials can be used for high temperature thermoelectric application. And on the other hand, the processing and scalloping of this oxide material is quite easy compared to the semiconductor-based materials, right? So in that aspect, we are also working on the variety of oxide materials like cobalt oxide and zinc cobalt oxide and zinc oxide like that. And this is some of the work I just want to show some of the results. And in the cobalt oxide, we just substituted the bismuth at different percent and study the impact of bismuth substitution on the characteristics, thermological characteristics. And for that, we just prepared the samples, and these are all the procedure which we follow for synthesizing the material. And these are all the pelletized bismuth substituted cobalt oxide pellets. And these are the exotic carton, this was substituted cobalt oxide. Look at that, the two samples shows in mixed phases of cobalt oxide, CO3O4 and CO2O2, COO. When the bismuth substitution occurs in the sample with multiple phases, it becomes a fluid phase of CO3O4, and then the bismuth is completely substituted, dissolved in the lattice up to 5%, and when it exceeds beyond 5%, there is a secondary phase formation of bismuth oxide that is also mentioned here, and that shows the solid solubility in the meat of bismuth is quite low in cobalt oxide, so that the secondary phase formation occurs in the sample. And these are all the further supportive studies for this substituted cobalt oxide that shows the thermal stability of the prepared material and the functional groups present in the material. These are all confirmed with the FAR and the TGL analysis. And these are all the same images of this prepared bismuth substituted cobalt oxide nanostructures. And the insert shows the pelletized image, and the sample shows the spherical morphology, and the particles are highly agglomerated, and the morphology is retained with respect to the bismuth content in the sample. And the XPS analysis confirms the mixed valence state of cobalt, and presence of bismuth and different state of oxygen in the sample. And the bismuth were 2 plus, the cobalt 3 plus and 2 plus were present in the sample, which confirms based on the spin electron splitting and wideness in the 2p and peaks of the cobalt 2p spectrum, and the bismuth substitution is confirmed by the presence of WFP. And the oxygen, lattice oxygen and surface oxygen present in the sample is confirmed by the SPH analysis. And these are all the electrical resistivity measurements for the bismuth-substituted cobalt oxide sample. And look at that, the two samples show slightly high resistivity. When the bismuth substitution is there, the resistivity has been reasonably decreased up to 10% of bismuth substitution, and slightly increased for 20% bismuth substitution. That's due to secondary phase formation of the sample. And of course, the carrier density is also quite reasonably improved. Although the carrier concentration is quite low, since it is oxide material, but still when the bismuth content increases in the sample, up to 2 orders, the carrier density has been improved, and the mobility has been increased with high carrier density. And the SIBA coefficient of the sample has been measured by placing the pelletized mass structure of the sample between the hot end and the cold end. And the Q1 shows the low SIBA coefficient, and when the bismuth substitution occurs, there is a rise in the SIBA coefficient, and especially the 20% shows the high SIBA coefficient compared to the other samples. And the power factor has been calculated by using this measured SIBA coefficient and electrical resistivity. And the power factor is also the 20% bismuth sample shows the high power factor compared to the rest of the sample. So that shows that the bismuth substitution is quite beneficial for improving the thermoelectric properties of the oxide. And similarly, we just tried for the bismuth substitution zinc cobalt oxide nanostructured material, and these are all the preferred nanostructured bulk pelletized material of the zinc cobalt oxide. And when the bismuth substitution occurs, whatever the structural changes are there, we studied by Charlie. And look at the first one is the pure zinc cobalt oxide pattern. And when the bismuth substitution occurs, the bismuth is completely dissolved in the lattice after 10% of bismuth. And when the bismuth exceeds beyond 10%, there is a secondary phase formation, right? And it's clearly observed here, and up to 10%, it's a complete solid solution, and it shows the alloying nature of the sample, the tunability in the lattice constant is observed when the bismuth is substituted in the sample. And the bismuth also influence on the morphology of the sample, starting from the spherical to the sheet-like morphology. The bismuth content increases in the sample, and that's what confirmed by this PSM analysis. And the morphology transformation of the retained in the pelletized nanostructures after the pelletizing of something at high temperature, so the particle and sheet-like structures are retained in the pelletized nanostructure sample as well. And this is the EDX mapping of this bismuth substituted zinc cobalt oxide. Look at that. The first one is the same image, and there is a white precipitate is there, and on the white precipitate there is a bismuth-rich composition was observed, and the rest of the regions are all the elements are homogeneously distributed. But on the white precipitate, the bismuth content is rich and with a reasonable content of oxygen. So that shows that the bismuth oxide precipitation, bismuth oxide secondary phase is also presented as precipitate in the parametric, and that is also supportive for the presence of secondary phases in the sample. And the sample has been subjected to the electrical measurements, and the pelletized nanostructure has been used for measure the carrier density, and the carrier concentration has been reasonably increased up to 10% of bismuth substitution, and slightly decreased at a high bismuth content due to the secondary phase formation. And the resistivity is also based on the carrier density. The resistivity also decreased compared to the two samples. The resistivity of bismuth substituted sample has been reasonably decreased and slightly increased for the 20% substituted sample. And this is the SIBA coefficient. The SIBA coefficient has been decreased for the sample as a function of bismuth content. When the bismuth content increases, the SIBA coefficient has decreased up to 10% and slightly increased for the 20% bismuth. And the power factor has been calculated, and it shows the 10% is the substituted sample shows relatively high power factor compared to the rest of the sample. And that for 10% is the substituted sample has been used to measure its thermal conductivity, and it shows relatively low thermal conductivity compared to the pure sample, especially at high temperature region. So with measured the thermal conductivity and Seeber coefficient in electrical resistivity, the ZT has been calculated, and since bismuth of shooter sample shows relatively high ZT compared to the Q sample. So that shows that the bismuth of shooter is useful for improving the ZT of the zinc cobalt oxide. So yeah, that's all about the thermal energy harvesting from the thermal energy, that is thermoelectric aspect. And another second aspect is the solar electricity. I just quickly go through the solar aspect. So as you know about the solar electricity, is one of the very useful technology to convert the energy from the solar energy. And the energy demand is another issue that we said in the beginning. So the depletion of conventional energy sources is one issue, and another one is the increasing world population and the increasing energy consumption. So that leads to huge energy demand for the present as well as future generations. So the sustainable energy technology is one of the solutions for the future. And the photovoltaic is one of the renewable and sustainable energy technology for generating the electricity from the solar radiation. And silicon is one of the dominant material for this kind of application, right? And these are some of the silicon solar cell. First one is the single crystalline silicon solar cell, and second one is the multi-crystalline silicon solar cell. And you can see the grain structures in the multi-crystalline solar cell, and that shows the polycrystalline nature of the base material. And these are the efficiency of the multiple different kind of solar cells. So there are different kind of solar cells. First generation wafer-based solar cell, second generation thin-film-based solar cell, and third generation multi-junction solar cell, and the emerging PV. So every year the energy, the efficiency is updated by the MERL, and you can find such kind of data in the Wikipedia itself, and you can see the progress of this technology. And look at that, the blue one is the silicon-based wafer technology. The slope is not at almost saturated, not improved drastically, and also for thin film as well. But look at this emerging field. So the slope is quite high, so the progress is very rapid. So even within the last 2 decades, there is a huge development with this emerging PV, including DSSC, DSSC, and the perovskite solar cell. And recently, the perovskite solar cell shows high performance even than the silicon-based solar cell. But still, there are some issues are there, and people are working on different aspects to solve those kind of issues. And these are all the kind of three different generations of solar cell. I just want to quickly show you some of the activities on emerging PV, that is the Dyson sized solar cell. And these are all one of the emerging PV. The Dyson sized solar cell is one of the low cost solar cell, and we can able to fabricate this solar cell in normal laboratory conditions, not like a silicon solar cell. And it's a quite economical one and cost effective one. And the efficiency can also be scaled up by properly doing the material science and engineering, and it can work in normal diffuse light as well, so perhaps we can able to use it for making smart windows kind of thing. And the problem with this Dyson solar cell is that it can able to absorb only the fixed wavelength of photons based on the homo-lumo level of dye molecules, and it has some poor stability of the dyes, poor chemical stability of dyes, and high corrosive nature of the electrolyte. All these things are limiting their applications. Okay. So the people are trying to develop different versions of Dyson solar cell by implementing different methodologies for making the photoanodes, photocathodes, sensitizers, and all. So these are all the methods for making the photoanode, like Dr. Blade or film printing or spray pyrolysis or film coating. You can use one of these methods to make your photoanode by using your metal oxide samples, and you can use it as a metal oxide coated substrate as a photoanode, and you can load the dye molecule over that, and by sandwiching with photocathode, you can fabricate your dye system. And these are the two versions of Dyson space solar cell. One is the solid electrolyte based and liquid electrolyte based. And the liquid electrolyte based shows the high performance, but still the leakage is the problem. So the leakage of the electrolyte is a problem for scale-up in this process. But to avoid that, the people have moved towards the solid electrolyte based DSC. But still, there are some recombinations and diffusivity. All these hindrances are there, so that the efficiency is not up to the level of liquid electrolyte based DSC. But still, the R&D is going on to improve the efficiency of solid electrolyte based DSC further. And these are all the procedure how one can scale up this solar cell. First, you have to make the cell, and from the cell you can make it as a module by connecting arrays of cells in the series, and then by connecting the module in the series you can make it as a panel, and then you can have an array. So like that you can make a large scale of solar cell, and you can use it for. So this is one of such kind of large scale Dyson solar cell developed at the Fraunhofer Institute, Germany. And like this, you can make some kind of flexible, foldable solar cell, so that you can roll it and you can put it in your bag, and wherever you want you can carry for kind of mobile chargers or iPod chargers like that. So we can use it for the localized application wherever you want. And these are all the components of the DSSC. There are a lot of choices are there for each and every component of DSSC. Like anode, you can able to use different kind of metal oxides, and you can make these metal oxides with different morphologies, like morphology, nanostructures, nanowires, nano rods, or spherical particles, like that. And dyes also, there are ruthenium-based dyes are there, and polypyrrolidine-based dyes are there, and that kind of organic dyes, inorganic imitators. Like that, there are different kind of variations are there in the sensitizer. The dyes are nothing but the sensitizer. And the electrolytes also, the polysulfide electrolytes are there, iodine electrolytes are there, like different kind of electrolytes are there. And in addition to that, some additives or treatment for these respective components will help to improve their performance. And the cathode materials also, the platinum is one of the expensive components in DSC. So if you want to reduce the cost of the DSC further, then you have to replace the platinum by carbon electrodes, and they're kind of low cost materials, so that you're going to be able to improve the high performance as well as reduce the cost. And these are some of the hierarchical nanostructured
Dear participants, sorry for the inconvenience. Due to some network error, our present chief guest got out. Few minutes, I will be back to the meeting. Sorry for the inconvenience.
Yeah, can you hear me?
Yes, sir, it's audible, sir.
Okay. I think there is a power cut actually here. The network was not working. Excuse me. Let me share this. Yeah. So I think the choice of materials, right? Okay. So can you see the slide now?
Yes, sir.
Okay. 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 So yeah, these are all the choices of materials for DSSC of different components, and we can make photoanode based on different kind of metal oxides with different morphologies, like rod-like morphology, particle-like morphologies, and all. And sensitizers also, we can use different kind of organic materials, organic dyes, like ruthenium-based dyes and other kind of materials we can use it as a dye molecule. And also, there's electrolyte also. There are iodine-based electrolytes are there, sulfur-based electrolytes are there. So, like that, there are different choices are there for each and every component of the DSCC, so that we can able to do a lot of modification in the device structure, and that will give you different performance. And these are some of the examples of these different morphology-based photoanodes, like particle-like morphologies, or rod-like morphologies, or branched rod-like morphologies, and how the electron transport occurs, the electron transport pathway through the interfaces in these branched rods, or well-aligned rod, or randomly aligned nanorods, a particle-like morphology of the photoanode. All these things can be realized by properly optimizing the synthesis conditions of the material, and that will lead to a variation in the transport behavior in the photon. And these are all the examples of branched nanorod structures that also